Good morning. This is Darrell Bruggink, Executive Editor of No-Till Farmer, and I want to welcome you to the first ever webinar that No-Till Farmer is putting on. And our webinar today is sponsored by GYPSOIL brand Gypsum. Today is actually the first in a series of 3 webinars on gypsum, and today's presenters are Ron Chamberlain, the lead agronomist and director of the GYPSOIL division, as well as Patrick McGinnity, who is the national sales manager for GYPSOIL. We have found that interest in gypsum uses and benefits are really quite high among no-tillers today. It's always been a very highly attended roundtable at our National No-Tillage Conference, and I can recall back in 2009 when we had our first ever classroom session on gypsum. Darrell Norton of Purdue conducted that classroom, and we had standing room only for that. So interest is really quite high. It's a good topic to hit. We've seen that in the last 4 years, our no-till farmer readers through our no-till operational benchmark study have shown that their use of gypsum has grown from 5% of our readership to today at 18% of our readers. So I want to thank you for being here, and I'm going to, with that said, I'm going to turn over the controls here to Ron Chamberlain. Ron, if you'd take it away.
Thank you, Darrell. Welcome, everyone. It's a pleasure to be here this afternoon. I've been an observer watching gypsum work on many thousands of acres with several growers for the last 11 years. And our earliest users continue to see soil improvements on their fields. Most of these farmers are actually no-tillers, and they're focused on soil quality, as are you. And I want to tell you, I really appreciate your efforts in no-till and your interest in gypsum. From the experience I have, I believe that gypsum is a tool that you should take a look at and consider for improving many of your no-till soils. Today we're going to talk about a few topics regarding gypsum. Gypsum as an important tool in no-till, a short history about gypsum in U.S. agriculture, what is gypsum, gypsum in a no-till system, and then some case histories of those who are using gypsum long-term. Gypsum is an important no-till tool. Interest is high among no-tillers because gypsum offers a couple of things that it does. First of all, amending soil quality and also providing nutrients to the crop. No-tillers obviously are aware of soil quality. That's why we're no-tilling, to improve soil quality, and we're all dealing with some common problems: compaction, ponding, sealing of the surface, poor rooting of the crop. Gypsum as a soil amendment actually builds soil structure and improves soils so that they're more manageable for field work. It makes soils less prone to compaction, thus it helps increase air and water penetration and reduces runoff and erosion. Gypsum as a nutrient source provides calcium and sulfur. As we know, sulfur deficiency is on the rise throughout our nation. Let's take a real quick history of gypsum. 200 years ago, Ben Franklin saw the beneficial effects of gypsum on his farm in Pennsylvania. He wanted his neighbors to learn about it as well. So every summer, at some point, he had a field on a hill that became brown and just wasn't doing very well because his soils were so compacted. So one summer late, he and some friends got together and they spread gypsum on that field in a very unusual way. In the following summer, when the field started to get brown, there in the middle of the field were the words, "This hill has been land plastered," where his crop grew thicker and greener. So obviously he got his point across, and the neighbors learned about gypsum. Gypsum historically has been used primarily on specialty crops. Only mined gypsum has really been available up until recently, and it was very expensive to mine and transport. So the high dollar crops were those that were used on gypsum. Gypsum was used on them, and they have good response to gypsum: potatoes, tomatoes, peanuts, and other specialty crops. But today, we have some new sources for gypsum. The Clean Air Act Amendment of 1990 required that coal-fired power utilities take the sulfur out of their flue gases. And so today we have what we call wet scrubbers at these coal-fired utilities, and they produce a synthetic FGD gypsum. Millions of tons of this are being produced throughout the United States, and millions more are projected to be produced in the next 20 years. There are also other manufacturing processes that produce synthetic gypsum. When food-grade citric acid and lactic acid and other types of food-grade materials are produced, synthetic gypsum is one of the byproducts. So, Patrick, tell us what's in gypsum.
All right, thanks, Ron. I'm going to talk a little bit about what is gypsum. If you remember back to some of your days in school, the professor may have mentioned that gypsum is a product that could be used in case you had heavy clay soils, and the use of gypsum would improve those soils. But that's about all that they had to say about the product. They moved on to the next subject very quickly. But today, gypsum's becoming much more of a valuable tool in crop production. And when we look at gypsum, let's first describe what it is. There really are two types of gypsum available. There is what's known as calcium sulfate anhydrate, and that's the type of gypsum that you commonly find on the west coast of the United States. And then there's a calcium sulfate dihydrate, which is the type of calcium you're going to find in the Midwest and as you move further east in the U.S. And this is a calcium sulfate molecule that's complexed with two molecules of water. And it's those two molecules of water that help in the solubility of the product, which increases the availability of both the calcium and the sulfur within the soil. A typical analysis for calcium or for gypsum would be about 20% calcium and about 16% sulfate sulfur. In other words, a ton of gypsum is going to have approximately 400 pounds of calcium for the plant and about 320 pounds of sulfate sulfur. When you look at gypsum, there really are several sources of it. The first one is mined gypsum, and it might be the one you're most familiar with. The problem with mined, or the challenge with it, is it's not very widely available. First of all, it's mostly concentrated in central Iowa or in parts of Michigan and in a couple of other states within the U.S. where they use kind of an open pit or strip type mining technique to mine the gypsum. Because of the fact that it is mined, it's fairly costly. It might be 2 times more per ton than synthetic gypsum. Because you have to freight it from the mine locations to where it's going to be used, the further away you get from the mine, the more expensive the product's going to be. Plus, when it's mined, you get a lot of variability in particle size. And it's that variability in particle size that's going to affect the performance of the gypsum. Because the finer the particle, the easier the gypsum is to dissolve, and as it moves into the soil profile. The larger the particle size, the less available it is, and the more slowly it dissolves. So you get a wide range of availability of the calcium and the sulfur through mined gypsum. When you look at synthetic gypsum, this is what I like to call the new or the environmental option. And I call it environmental because, first of all, you're not practicing an open pit or strip mining and destroying the landscape. But secondly, you're taking what used to be a waste byproduct and you're putting it onto agricultural soils and help to improve crop production throughout the United States. There really are 3 sources of this synthetic gypsum. The first one is recycled wallboard, and it's exactly as it states. It's drywall or wallboard tailings from the manufacturing facilities or from large construction projects that are gathered up, ground down, and applied to the soil. The good thing is it does supply calcium sulfate. Bad thing is with that is you also have to cope with some of the binders and the paper that's part of that wallboard, which can affect how easily it's spread or can also affect the availability of the product. The second source is it comes from a manufacturing byproduct. It comes from both a citric acid manufacturing plant or a lactic acid manufacturing plant. And these are food-grade plants that produce citric acid and lactic acid for incorporation into foods. And one of the byproducts of it is calcium sulfate. The third one is what we call FGD gypsum. It's the flue gas desulfurization gypsum that comes from coal-powered fire plants. And that's where the sulfur dioxide gas that evolves from burning coal is trapped and is turned into calcium sulfate. Well, there's a company, GYPSOIL, who I work for, that is establishing a growing network of supply partners that include these coal-fired power plants and food-grade manufacturing plants. We're structuring relationships with these people that have this type of waste byproduct that up till now have been landfilling it, and we are becoming their marketing partner, and we're distributing it to agricultural distributors, traditional ag retailers, and then to the ultimate end user, the farmer himself. Here on this slide, you'll see that we've got partners in Wisconsin, Indiana, Illinois, Ohio, as well as several other states in the Midwest. And we also have relationships in the Southeast and the Mid-South parts of the U.S. You see some of the brands of these power companies and food grade manufacturing plant companies. You might recognize some of those from your own area. When you look at FGD gypsum, which is the one that we're primarily talking about today, it's really a process where we start with high quality limestone in the process. And first, this exhaust that comes out of the coal-fired power plants, the particulate is first removed from it, and the nitrous oxide is removed, and then the limestone or the calcium carbonate is used to trap the sulfur dioxide. What you really have is a two-step process. First part, like I mentioned, limestone or the calcium carbonate is combined with the sulfur dioxide gas. And what you get is calcium sulfite, and CO2 then is given off as a byproduct. And when you take the calcium sulfite and react it with water and oxidize it with some oxygen, the end product is calcium sulfate dihydrate, which is what I described to you in the beginning as gypsum. And through this two-step process, we get a significant supply and source of gypsum for the farmer to use. The thing about FGD gypsum, as Ron has talked about, is since the 1990 Clean Air Amendment Act was passed, the level of sulfur in diesel fuel and the level of sulfur in coal-fired power plants was forced to be reduced. As a result, we have supplies that are expanding as we speak because more coal-fired power plants are coming online, more efficient scrubbers are being in place, and what we get then is a significant supply of FGD gypsum that we can distribute to the farmers. The FGD gypsum is a carefully regulated product, and it's regulated on a state-by-state basis. It's kind of a two-step regulation process. The first one is getting permission from the state pollution control agency, and it varies by state what they call that group, getting permission to apply this byproduct to agricultural soils. And the second step is once it's been approved to apply this byproduct to agricultural soils, the next step is to register with the Department of Agriculture in each state, either as a soil amendment or as a fertilizer, depending upon the state's requirements. And GYPSOIL has become a primary liaison with these types of suppliers of this raw material to provide FGD gypsum to the end-use grower. The characteristics of this gypsum, in FGD gypsum in particular, it's a fine tan powder, and if you put it in your hand, you could form it into a ball that's rather damp to the touch. It's about 8 to 10% moisture when it goes out into the field. When you look at gypsum from a manufacturing process, it's more of a white to a gray powder, very finely divided, real fine, uniform particle size, and its moisture can range from 8 to 15% depending on where it's stored. The physical properties of these types of products varies depending on the source. As I mentioned, from the manufacturing process gypsum, very finely divided powder, and the FGD gypsum, also very finely divided, but a little bit different in color, a little bit different in texture. And it's really this fine particle size that makes FGD gypsum so highly reactive in the soil, and that's why you see such a response to it when it's applied to an agricultural soil. The finer the particle size, the higher the reactivity, and the faster the dissolution of the product's going to be. When you apply it to the soil, moisture is applied to it, and it starts to move into the soil profile. And it's that reactivity and that dissolution rate that makes the calcium and the sulfate sulfur available to the plant and puts the gypsum to work amending the soil. Let's talk about some characteristics of gypsums that maybe we've heard about in the past that aren't true. Gypsum, for example, does not affect the soil pH. It is not a liming agent. It's calcium carbonate is the liming agent, and that's what you use on an acid soil to raise your pH. But gypsum does not affect the soil pH. As I mentioned earlier, it's this fine particle size of the gypsum that makes it very highly water soluble and allows for easy movement into the soil profile. It really makes gypsum ideal for a no-till farming situation. There are some misconceptions out in the field about FGD gypsum, and to look at that, I think what you need to look at is what I'm going to call old FGD gypsum, and this is some of the original scrubbed sulfur dioxide and some of the original gypsum that was produced from those scrubbers. And we're going to compare this to what I call now the new FGD gypsum, and that's the type of gypsum you're going to get today from an FGD plant. The original stuff, the old material, contained a lot of fly ash element, And in that fly ash, there were residues of heavy metals such as arsenic, selenium, and several other ones. And this varied by the source, and there was some concern about those heavy metals in agriculture. The new FGD gypsum, the fly ash is first removed, and the resulting product is very low in trace elements, and it's really hard to find potential adverse effects from this new FGD gypsum. As I mentioned, very low in trace elements and other contaminants, and there were concerns with the old material that there was significant concentrations of mercury in there that might prohibit its use on agricultural soils. But with the new FGD gypsum, this hazard potential is very low, and the USDA has looked at this with great detail and has found no concern for the concentrations of mercury that are in the new FGD gypsum product. To support that, let's take a look at this chart. This chart looks at a lot of heavy metal pollutants that the EPA regulates in waste byproducts. If you look at the first column, we look at the pollutants starting with arsenic, cadmium, copper, lead, mercury. The second column establishes the EPA limits, or shows the EPA limits that have been established for these types of heavy metals in waste byproducts that are going to be applied to the soil. We took a typical sample from Wisconsin Energy, and you'll see that in Wisconsin Energy, either on all these materials that we evaluated, the levels are either below the detection limit or are well below the threshold levels established by the EPA. In fact, if you look at the levels of the Wisconsin Energy product and take it as a percentage of the regulatory limit, we're well under 2% at the highest level of any of these contaminants that might be present in the FGD gypsum. So FGD gypsum, in conclusion, we feel is really safe and effective. And GYPSOIL as a manufacturing partner does maintain a rigorous quality control program for all the products that are sold. We test for moisture, we test for purity, percent calcium, percent sulfur on all the gypsum products that we carry. We also make significant investments in field performance of these products. Ron, the person that opened up the talk, is in charge within our company of coordinating university trials around the country to demonstrate the effectiveness of gypsum in terms of providing calcium and sulfur to the plant, as well as through years of use amending the soil. With that, I'm going to toss it back to Ron, and Ron's going to talk to you a little bit about gypsum use in no-till systems. Ron?
Thank you, Patrick. Gypsum in a no-till system. Let's take a look at the amendment portion. Gypsum actually increases soil particle aggregation. What does this mean? We take a soil like the one on the left that's compacted. There's very little air in that soil. Roots have a difficult time penetrating through that soil. It tends to pond if it's in a flat area. It tends to erode if it's in a hilly area. And gypsum changes the structure of that soil, increases particle aggregation. That same soil on the right, as you can see, is very friable. It's very aggregated. It's biologically very rich. It's moist. It's just a really good environment for plants to grow. Well, that's what gypsum does. So if we're dealing with soil structure, let's talk about that for a second. What makes up soil structure? Well, if we look at the diagram here, that represents the clay particles and the organic matter in the soil, and those are covered with negative charges, almost like a magnet. They attract positive charged nutrients, potassium, calcium, hydrogen, magnesium, ammonium, micronutrients. All of those are attracted to those negative sites, and it's from those sites that the plants can source nutrients that they need. Well, another thing is happening here. As you look at the calcium in the center of this, it's got a double positive charge. It tends to hold these clay particles together in an aggregate. Now, it's not always that way. Magnesium, for example, works a little bit differently. Magnesium also has a positive double charge, but it attracts water around it. We call bound water, and that water prevents the clay particles from binding tightly to the magnesium, and so those are dispersible. Those particles can be dislodged with very small amounts of energy. For example, when a rain droplet hits one of those clay particles, it will remove it. It will dislodge it, and it will be dispersed from that colloid. That clay particle will then go into the water that's on the surface of the soil, and as that water moves down through the soil, the clay is filtered out, and we end up with a skin seal, a sealed surface on that. So this is a bad situation. If you drive over that colloid, that soil colloid with an implement, for example, it will become compacted and remain very, very compacted. So again, this is what we do not want, and this is oftentimes the case, what we do have in our fields based on too much magnesium, for example, or too much aluminum or too much sodium in the soil. So if we take a look on the right-hand side, that diagram represents what we call flocculated soil, and this is soil that has good structural stability, and it has that because the calcium double positive charge can hold those clay particles together very, very tightly. They're bound tightly enough that that soil has good structural stability, and as a result, the soil begins to aggregate. So we want to have a sufficient amount of calcium in the soil to accomplish this, and we want to not have excesses of magnesium or aluminum or sodium in the soil, which create the bad soil characteristics. So how do we accomplish this? Well, interestingly enough, gypsum is really the only tool that can provide this function in this way. Gypsum, calcium sulfate, like Patrick mentioned, spread it on the field, get rainfall, water. Right away, the calcium dissociates or unhooks from the sulfate sulfur, and the sulfate sulfur then binds up with the excess magnesium that's in the soil, creating Epsom salts, which is a very soluble material, and it moves down into the soil profile below the rooting zone. And the calcium then that's left over replaces the magnesium. As you see on the right hand end of the arrow, the calcium now holds these clay particles together very, very tightly. And now we have the beginning of this soil getting better, aggregating and having a better structure. So that's, in a few words, that's what gypsum does. It's a very simple process. Results are improved soil structure that will allow soil biology and crop rooting to grow prolifically. It also allows rainfall to move through that soil profile, allowing oxygen to follow to help feed that soil biology and that crop root. Gypsum in a no-till system, then as a result, we see significantly less ponding on our fields because the water is moving into the soil, not down the hills into the ponds. So as a result, we have more working days between rainfall events at critical times throughout the year, the spraying season, the harvest time. Gypsum in a no-till system improves water infiltration. This slide represents some work done by the National Soil Erosion Lab at Purdue University, and it's showing us steady state water infiltration into the soil and through the soil in inches per hour along the left-hand side. Across the bottom, it shows the percent base saturation of calcium. So basically what it's showing with the gray bars is as we increase the calcium levels in the soil up to the optimal level, which is 74%, we increase the water infiltration significantly from 1/10 of an inch per hour to 1/2 an inch per hour. So it increased it 5 times. Even 1/2 an inch per hour, though, is still not enough infiltration in many cases. So the green bars then are showing us the impact that gypsum has in this environment. And essentially, where we're using gypsum as this calcium source to flocculate these soils and to cause them to aggregate, you can see that with the calcium balance at 74% and gypsum, we have increased the water infiltration 18 times above what it was with just the calcium at an insufficient level. So bottom line, these soils will allow 1.8 inches of water to infiltrate and move through that soil every hour during rainfall events. And as long as there's somewhere for that water to go, it will allow that. And this is what I'm seeing from a commercial standpoint over the last 11 years. This is exactly what's happening in these fields. This soil has almost become like a sponge, and we don't see the ponding because of the soils being able to absorb that water. In a no-till system, gypsum obviously then can help control erosion. If the water is going into the field, instead of off of the field, then that reduces the amount of soil loss. And this is some work done showing the amount of soil loss per plot in a tilled plot environment and in a no-till plot environment. And essentially what it's telling us is the tilled plot environment with the white bar, which is no treatment, we have 9 kilograms of material being lost off of that plot. By adding gypsum in the tilled plot, which is the gray bar, we've reduced that soil loss significantly. And if you look over to the no-till plots on the right, the white bar, again, has significantly reduced the amount of soil loss just by no-tilling the field. And adding gypsum into that environment reduces that even more. This is erosion control is a real issue around the world. These photos represent an area in New Zealand that has been barren for a long, long time that they have brought back into production using gypsum. Gypsum also reduces surface crusting on the field. In the springtime, when we've worked the ground, we've got the crop in the ground waiting for it to emerge. We get a rainfall, and suddenly we've got a sealed surface. What's happening there? Well, essentially, the soft rain droplets have come in contact with the soil. They become hard. They take a nutrient off that soil, and that allows that clay particle to break loose, like I showed you earlier. And as that muddy water starts to infiltrate down through the soil surface, the clay is filtered off and remains on the surface in a real tight seal, about a 3/8 of an inch thick layer of clay that prevents air from moving into the soil, as represented in the top slide. Unfortunately, when air can't get into the soil, then the water that's in the soil from the rain can't get away, and so we've got a waterlogged environment. And if we've got seeds in the ground or seedlings trying to emerge, that's a real issue. But when we put gypsum in that environment, have it laying on the surface, the soft rain droplet is satisfied. It gets its nutrient to become hard water. It gets it from gypsum. And so that allows the aggregated soils that gypsum has helped aggregate stay in place. There are the pore spaces now down between those aggregates that allow the water to move down through the soil surface, and oxygen follows, and then the soil biology then responds to that. In a no-till system, then obviously, if we're preventing soil erosion because we're not getting the water runoff, it also has an impact on nutrients. Again, more work done by the Soil Erosion Lab at Purdue. Essentially, what they're showing us is the blue bar is the amount of water that is running off of the field in a rainfall event. Adding gypsum into that environment reduce that water runoff by 20%. The tan bar represents the amount of soil loss due to the water running off. And that soil loss has been reduced by almost 60%. The green bar represents soluble reactive phosphorus. This is the phosphorus that is mobile in the soil, the phosphorus that you have purchased and put on the field. It's mobile in the soil, and it moves off the field with the soil and the water. And so by keeping the soil and the water on the field with gypsum, we've reduced the loss of soluble phosphorus by 75%. So it has a huge impact on the quality of the soil by keeping the soil intact on the field and on the valuable nutrients that we need to raise our crops staying on that field. There's another impact as well. Obviously, when the soil runs off of the field, it gets into our water streams, moves into our watersheds, and ultimately is deposited in a lake or in the Gulf of Mexico, and that's a real environmental problem. The photo on the right is Lake Erie in the springtime during rainfall events, and the brown is the polluted water, essentially, with sediment and nutrients that has flowed into Lake Erie from the Maumee Basin. The green and blue are algae blooms that are forming as a result of the nutrients that are in that. So it's a real environmental issue for these lakes that is expensive for us as farmers, and by reducing that runoff, we can reduce the impact on the environment as well. Gypsum improves water holding capacity. Now, how does it do that? Well, the slide here kind of represents the results of that. The field on the left is a cornfield. This is in 2008 in late August during a drought not nearly as severe as we're experiencing this year, but a drought nonetheless. The field on the right, the neighboring field, is showing drought stress. The field on the left is not. The field on the left has been treated with gypsum for 5 years. It's a no-till field. The field on the right has not been treated with gypsum. And essentially what we're seeing here is that for whatever reason, the plants on the field on the left are getting adequate moisture to respire and stay cool and continue to grow. And the reason those plants are able to do this is because as we dig down in the soil profile, we're finding that the gypsum has flocculated that soil deep down into the soil profile. And if you look at the water holding capacity of the soil, that is the surface area of the soil, the water that attracts to that. And if that soil is compacted, you have very little water holding capacity. But if you aggregate that soil, you increase the water holding capacity per unit of soil by as much as 20%. So in each layer of soil there, we have 20% more water, but also because the gypsum is moving down through the soil profile, we have many more tons of soil to hold that water deep into the soil profile. So certainly that makes a huge difference in terms of hot, dry years where we need a reserve capacity of water in that subsoil and the ability of the plant to reach down and pull that up. This is a look at what's happening. Gypsum is building the soil profile and it enhances the soil biological systems. And as we move down through this profile, the upper 12, 14 inches of topsoil has become very, very aggregated. And as we move down into the middle subsoil, it runs from about 14 to 28 inches deep in the center picture. Where we in the past had not really had much happening there, we now have night crawlers and earthworms, corn roots, a lot of activity going on in that middle picture. The picture on the right is actually down almost 5 feet into the subsoil. Because the gypsum has changed the soil structure and moved down through the profile, accomplishing this, the earthworms have followed it down. And as they break down residue, they take it down deep into the soil. They deposit it as black organic matter. And ultimately, we have an area for the crop root to go to get nutrients, moisture, and oxygen in some of the most critical times during its growth. So what we have here is a permanent change in these subsoils if we continue to manage that soil in a proper manner with no-till, with gypsum, with cover crops, other things to keep that open, keep it alive. So certainly a very important resource there for the soil biology. And obviously we're encouraging their growth, so we see faster, more complete residue breakdown as the soil earthworm populations increase dramatically. We see that breakdown happening and converting those plant materials into usable nutrients and humus for the next crops. Gypsum can reduce phosphorus runoff, and the USDA is doing some research in the Chesapeake Bay in Maryland to demonstrate that. Here we have a trench 5 feet deep in the soil. They have filled it with gypsum, and now the water that moves from the field on the right across the surface of this gypsum and the subsurface water that comes through the column of gypsum to the ditch actually have the phosphorus bound up by the gypsum. The phosphorus stays behind, and the water is much cleaner than that moves into Chesapeake Bay. In many cases around the U.S., we have sodic soils. Sodium ruins soil structure. Sodic soils are caused by just the natural parent material in some cases. In other cases, it's caused by irrigation water that is depositing sodium on the surface. Whatever the cause, the soil structure is ruined. What we know from gypsum is that when we apply gypsum to these situations, the calcium actually displaces the sodium off of the soil particle, and then additional rainwater and irrigation water flushes that sodium down into the subsoil away from the rooting zone and allows those soils to aggregate once more because they have calcium, adequate calcium on there to aggregate. So the soil structure comes back, and then these soils become much more active and productive. We have another problem in our soils, and that is aluminum toxicity. All of our soils have aluminum, and the toxic aluminum becomes very, very available as the pH goes down significantly. So in many cases, we have subsoil pHs that are below 5, and that releases the aluminum. And unfortunately, aluminum destroys the root tip of the plant. And so with the aluminum there, we cannot have roots penetrating down into that profile of the soil. By removing the aluminum with gypsum, then the root tip is free to grow, and we get roots down into the profile. So to illustrate this, we have a crop growing, we have rooting. On the left side, we've got the aluminum at the in the acid soils, and we have no roots growing into that. Come along, apply gypsum. The calcium removes the aluminum, it flushes down deep, and then the roots can grow deeper, giving us a much greater mass of roots for supplying that crop. Gypsum, in this case, work done at The Ohio State University shows that applications of gypsum takes those toxic levels of aluminum down to less than half, and that's into the areas where they're not as toxic. Gypsum as a nutrient source, gypsum contains 16% sulfate sulfur, and sulfate is the form of sulfur that plants use, so it's readily available. It also provides 20% calcium. Now let's talk about sulfur for a minute. I mentioned in 1990 the Clean Air Act forced the utilities to remove sulfur from their flue gases. These two maps show the deposition of sulfur, brown being high levels, in 1985 and then again in 2008. And as you can see, the amount of deposition has been dramatically reduced due to the wet scrubbers that are put on these power plants. The Ohio State University has been tracking sulfur deposition from the atmosphere since 1979, and it's a straight downward trend in less and less. In 1971, there were 30 pounds per acre of sulfur being deposited, which is adequate for many crops. By 2002, that was cut by almost half. Today, another 10 years later, it's even lower. So as a result, we're seeing deficiencies showing up in many of our soils in many of our states. Gypsum as a sulfur source fills in that gap. As a calcium nutrient source, 20% calcium in gypsum is ideal, especially because it's water soluble, moves down into the soil. And crops such as melons and tomatoes and potatoes need a high amount of calcium for their skin quality, for the quality of and the storability of these products. Peanuts need lots and lots of calcium in order to actually form the nut in the shell. So gypsum is used in these specialty crops in this way to help improve the amount of quality and quantity that we get from them. So let's take a look at some folks who've been using gypsum for a number of years now and kind of see what they have to say about gypsum. Jack Maloney in Brownsburg, Indiana, farms 2,600 acres of corn and soybeans. He is a no-tiller and started applying gypsum in 2002. Jack has seen improved soil structure and water infiltration, giving him better soil and water quality. He is in a watershed where there's been research work done, and the research work has shown that the nutrients that are being lost from his field through drain tile are roughly 1/3 of the nutrients that are being lost in the rest of the watershed from the other operations. So significant difference there. He's also seeing improved yields and lower production costs in terms of equipment, labor, fuel for tillage, and fertilizer costs. Hessian Farms, again near Brownsburg, Indiana, 5,000 acres of food-grade corn and soybeans. They're in a strip till environment. They started applying gypsum in 2005. They're finding improved soil tilth, many more earthworms, giving them more air and water channels to work with. And as a result of the soil biological activity improving and balancing their nutrition, they have lowered their P and K applications by 25 to 30%. Rulon Farms in Arcadia, Indiana. Rodney farms 6,000 acres of corn and soybeans in a no-till operation. Started applying gypsum in problem fields 7 years ago to see what it'll do. With the results of those fields, he expanded to 3,000 acres in 2010, and now he's using it on the entire 6,000 acres. Rodney sees improved water infiltration in his farms, which is essential under the weather conditions that we're dealing with in the last few years. Rodney says keeping water for the plant has a benefit to the yield. He knows this. And fertilizer is terribly expensive, so there's no reason to let it leave our farm. Let's keep it on the farm. Let's use it and allow that crop to grow to its best potential. Rodney will be a presenter on our August 16th webinar, and also will be the host site for the Midwest Soil Improvement Symposium, August 21st. So we would encourage you to join us in the August 16th webinar and sign up for the Soil Improvement Symposium at www.gypsoil.com. Scott Stoffel is a dairy farmer in West Bend, Wisconsin. He started applying gypsum in 2010, first to his alfalfa, then to his soybeans. Sulfur has been an issue of deficiency, and these two high protein crops need sulfur, and so that's where he started. He knows it's critical to his crops, and he's finding that his feed test of sulfur is going up, and his cows like that. Finally, Brad and Jacob Brown of Center Point, Indiana. They farm 900 acres of corn and soybeans. They're no-tillers also. Their soils are flat, very poorly drained silty clay loam soils. They started applying gypsum in 2005 to try to improve their drainage. And as a matter of fact, they find that they have improved water permeability on the poorly drained ground, which is the majority of the farm. And they also see that sulfur is helping get the crop going early in the year. And Jacob and Brad are both very pleased with their no-till and with their gypsum. So with that, we'll take questions.